Codewars.com has an interesting problem called Faro Shuffle count. Basically, we get a deck of playing cards and we split the cards into two, and then we shuffle them. And the shuffling process is in a perfect arrangement. Basically, you will see cards from each half placed or stacked on top of each other in a perfect configuration, and we are asked to find out the number of shuffling required to get the cards back to the original arrangement. And this example here is really explaining this problem here. So I call it first shuffle. So we will split the cards into two halves. In this example, I have 8 cards. So cards 1 to 4 are in the first half. Cards 5 to 8 are in the second half. So after the shuffling, we will see the, I'll copy it. We will see the first card on the first half is on top, followed by the first card in the second half, and then second card in the first half, and second card in the second half, third card in the first half, third card in the second half, fourth card in the first half, and second card in the second half. So this is the orientation after the first shuffle. So you go with the second shuffle. Again, you split the cards into two halves. So the first cards in the first half coming here, the first half in the second, the first card in the second half comes over here. Second card in the first half comes over there. Let me do it one more time. First card in the first half. First card in the second half. Second card in the first half. Second card in the second half. Third card in the first half. Third card in the second half. Fourth card in the first half. And finally, last card in the second half. This is after second shuffle. And once we do the shuffle one more time, so first card in the first half, first card in the second half, second card in the first half, second card in the second half, third card in the first half, third card in the second half, fourth card in the first half, and fourth card in the second half. Guess what? We come back to the original orientation, original formation. Well, this suggests that if you have 8 cards in the deck, if you do back-to-back 3 shuffling, you will reach back to the original formation, okay? Original order of the decks compared to the beginning state. So we will be putting together a code explaining that process. So in the solution window, it starts with this. So I'll just copy it and I apply it on Colab. I like to do that because I can put print statements before I'm completely done, and I can see the end results without getting error messages. Right? This is my working file basically, but I will still put together a function. Well, in order for me to run the function, I need to have it the command for Faro cycles, and I need to give the n number for deck size, right? So let's start with first generating the cards in the deck. And I call this M. It's an array. And I can use the list comprehension method here. So I can call X for X in range, and I can give the deck size. And that's my first, that's my really the cards in the deck. So I can print it out. Print statement, let's call it cards in the deck. And I assign this variable M for that. So if I run this now, so I have to give a number here. So let's go with 8 as the example we went through on Google Sheets. Okay, so cards in deck are having an index or indices starting from 0 all the way to 7. We have an array with a length of 8 elements, right? Now, we are asked to report the number of shuffles required. So I will start with a counter, and I will call it shuffle counter, and it will start with 0, right? So I will start shuffling. Well, I don't know how many times I need to do that for different deck sizes. So I suggest we do a while loop here. Basically, we will just keep on shuffling until we see that cards are in the same formation after a number of shuffling. So every time I do the shuffling, I need to increase my counter. So I will have this shuffle counter increased by 1 with the shuffling process. So we can say print shuffle counter, and I will assign shuffle counter for that. Right. So when I do that, I get this error message because I forgot to put the column here. Okay. And unexpected indented. Hold on. I think Python is very sensitive to indentation, so I fix it. Okay, should be okay now. All right, so I just stop it. So this is a continuous loop. So basically what I'm doing is I am running it continuously without having any work inside the while loop, so it will go forever. So what I will do is I will first split the deck into 2 halves. So I'll call it half 1, and this half 1 is basically an array or subset of array M with indices starting from 0 all the way to deck size divided by n. So if we have 8 cards, the first half will include the cards with indices up to 4, excluding 4. Well, if I run that, I can show you here. I'll get an error message because sorry, I forgot. Why did I put n here? I need to put 2. I'm sorry. So when I run this, I'm getting an error message. It says the list indices must be integers or slices, not topic. Well, my understanding is that in this case, if you divide the deck size to an integer, the end result is a float, and you cannot use floats as indices. So we need to convert it to integers. So in this case, it will be 4.0 as float, but with an integer, it will just be 4, and it should work now. All right, so let me find out the mistake. Okay, of course, I made the mistake in here as well. So I need to put column for the indices. If I put a comma, these are becoming tuples, right? All right. or and it goes so no, this now works. We get that figured out. Let me go back. I have to stop it. All right. Now I will do. I can just print it and show print and call it cards in first half, and I will report fun over here. So that works. Okay. So we have infinite loop, and on each loop it shows that we have an array with 4 elements from indices 0 all the way to 3 included, right? So I need to generate the second half. So I just copy it over here and called it half 2, and cards in the second half. All right, and half 2. So this time the indices should be from where I stopped in my first half all the way to the deck size. Okay, let's give it a try. All right, awesome. So the continuous loops it's just adding shuffle counters non-stop and reporting the cards in the first half and second half. So everything is good. So we have cards indices from all the way 0 to 7. First 4 are in the first half, and the last 4 cards are in the second half. Okay, so this so far works fine. So what we have to do is we need to rewrite or regenerate the cards in the deck, but we have to start from an empty array. So I will now inside end loop, I will assign an empty M list. So I'm just erasing what we had documented so far, and then I say for I in range deck size one half, and again I need to make it inside an integer statement comment and put this column here. I will append to the array M, this empty array M, the elements of the first half and the second half. I have to use parentheses for the append command. I will first add the element from the first half, and then add the element or append the element from the second half within this index of I. Now, if I do that, run it. Okay, I can stop here. Let me go all the way up. It's probably cut over there. Okay. So I will be adding M's, but I need to first write down this print statement, and it should be outside of the for loop because I would like to write the see the deck after shuffling. And I put down M here and stop. All right. So it's just the same loop all over again, showing the cards in the first half, second half, and deck after shuffling. It does the matching element-wise shuffling that we discussed on the Google Sheet. So first element of the first half here, first element of the second half here, second element of the first half, second element of the second half, third element of the first half, third element of the second half, fourth element of the first half, and second element of the second half. Right. So it works, but the problem is it never stops. So we need to stop this while loop when we get when we meet a condition such that this generated array M becomes identical to the original M we had in the beginning. So we have to put this condition to the while loop to stop the iterations. And what we can do is we can just put an if statement and say if the rearranged array M becomes identical to this M, which is defined by that list comprehension here, we say break this column here and break. Now, with that, this continuous loop will stop when we have this condition met. All right, so I think it should work now. Let's give it a try. All right, awesome. So let's read the output together. It shows the cards in the deck here from this print comment. We generate the original formation of the cards in the deck here. We generate that and we print it out. And we put our shuffle counter start with 0. So the while loop starts. So our first shuffling takes place. After the shuffle or before the shuffling, we have the first half of the cards here and second half of the cards here. And after shuffling, the orientation of the elements in the deck are as follows here. All right. And inside the while loop, this condition is checked. Since we haven't met this condition, while loop will continue with the second shuffling, and this will be the orientation of the cards after the second shuffling, and then third, and the third one, if you pay attention, that is really what we had in the beginning. So we can stop shuffling after the third one. So in this case, if we have 8 cards, we need 3 shuffling required. Now we can play with the data and we can, let's say, do it for 10 cards. And for 10 cards, we would require 6 shuffling. And in the problem definition, okay, if 8 perfect shuffles are performed on a deck of 52 playing cards, the deck is restored to its original order. Let's check it out. I'll put 80 to 52 here and do the shuffling. And we have a longer list this time. And yes, 1, 2, 3, 4, 5, 6, 7, 8. After the 8th shuffling, we bring the cards back to the original order. That is how I put the codes together for this Faro Shuffle cycle. But there are way more creative or more effective methods, but this is a part of learning process, and I will be comparing this to them and try to improve my Python skills.